Now that you've seen the power of DSLs in action, let me show you how they are exactly built. Internal DSLs are constructed using four core design patterns that work together to create flexible, composable systems. Understanding these patterns is crucial because they appear in almost every successful DSL. Now, let me walk you through each of these patterns. The first pattern is called combinators, and it's the mathematical foundation that makes DSL possible. A combinator is a function that takes programs as input and returns new programs as output. This simple concept enables unlimited composition. Now, here's the basic structure. Let me break this down for you. We have an interface called processing step with a single method process that takes a dataset as input and returns a dataset as output. This uniform signature is crucial. Every processing step, no matter how complex internally, looks exactly the same from the outside. The magic is in the and then method. This is our combinator. It takes two separate processing steps and creates a new processing step that combines them. Look at what it returns. This is the this is a lambda that first applies the current step, then takes that result and applies the next step. The beautiful thing is that the result is still a processing step. So we can keep combining indefinitely. Now let me show you how this enables flexible composition. Here's our filter step implementation. Notice how simple this is. We store a predicate, a function that tests whether a record should be kept or not. In the process method, we're calling filter on the input data set with our predicate. All of the complexity of how filtering works is hidden inside the dataset's filter method. Similarly, our transform step stores a transformation function that takes a record and returns a modified record. The process method applies this transformer to every record in the dataset using a map function. Now, watch what happens when we combine them. If you look at the first three lines, we are creating three different processing steps. The email filter step keeps only records that have an email field. The add country step adds a country field. And the age filter keeps only records where the age is 18 or older. And in the next, few lines is where the actual magic happens. We can create different pipelines by combining these same components in different ways. The basic pipeline just filters for email and adds country. The adult pipeline does email filtering, then age filtering, then adds a country. And the senior pipeline filters for age, then filters for seniors, and then adds a senior discount. The key insight is that each of these combined pipelines is still just a processing step. From the outside, basic pipeline looks exactly the same as email filter. They both have the same process method signature. This uniform interface is what makes unlimited composition possible. Why does this work so well? The combinator pattern gives you three crucial properties. First, you get a uniform interface. Every processing step looks the same from the outside, regardless of its internal complexity. Second, you get referential transparency. You can replace any step with an equivalent step without affecting the rest of the pipeline. And third, you get infinite composability. Since the results of combining steps is still a step, you can keep combining indefinitely. The combinator pattern transforms your programming model from write procedures that do things to build components that can be combined to do things.